Hello, this video covers electron configurations. So we're on page 10 of the notes. If you have any questions, just to ask. If you need to check the learning outcomes, they should be available in Google Classroom. So the arrangement of electrons in the energy levels and the orbitals of an atom is called the electronic configuration, and there are different ways that you can represent this. So the first way we've met already, which is using quantum numbers. So remember that every electron in an atom has a different set of 4 quantum numbers. So no 2 electrons can have the same 4 quantum numbers. So this is the quantum numbers describing the 3 electrons in lithium. The first electron is in the first energy level. It's in an s orbital, which will go ml and also a value of 0, and the spin is +1/2. The second electron is in exactly the same orbitals, but has the opposite spin, -1/2. The third electron is in the second energy level, in the s subshell, which gives ml a value of 0, and has a spin of +1/2. You can also be asked to represent the electron configuration using orbital box notation. So each orbital in an atom is represented by a box, and each electron is shown by an arrow. The boxes are filled in order of increasing energy. So for example, the first 2 electrons in lithium occupy the 1s orbital. The third electron in lithium occupies the 2s orbital. You should always put the names of the orbitals underneath your boxes. The boxes alone with the arrows in them aren't enough at advanced higher level. And finally, the spectroscopic notation uses a shorthand way to represent the arrangement of electrons. For example, carbon has 6 electrons. In the 1s orbital there are 2 electrons, so this 1 represents the first energy level, s for the orbital, and that 2 shows that there are 2 electrons in it. 2s2 means there's 2 electrons in the 2s orbital. 2p2 means that there are 2 electrons in the 2p subshell. If you have elements with lots of electrons, you can make the spectroscopic notation shorter. So instead of writing out all the way from the 1s all the way to whatever electron shell that you're filling, then you can use a noble gas shorthand. Now in an exam, do not use a noble gas shorthand unless it says that it's acceptable to do so. Okay, you should always give the full spectroscopic notation in an exam. So for example, neon is 1s2, 2s2, 2p6. Sodium is 1s2, 2s2, 2p6, 3s1. Okay, so it's got exactly the same starting electron configuration as neon, and there's 1 electron in the 3s orbital as well. So you have to write the electron configuration for an oxygen atom in terms of s and p orbitals. So the electron arrangement, it will have 8 electrons. You can add up these prefixes, by the way, and it will tell you how many electrons there are. For example, here, neon has 2 electrons plus 2 electrons plus 6, 10 electrons. So sodium has 2 plus 6 plus 1, 11 electrons. Okay, so if we look at the configuration for an oxygen atom, it will have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and then in the 2p orbital, remember the p subshell can hold up to 6 electrons, there will be 4 electrons. You should now be able to complete questions 15 to 18 in the inorganic chemistry section. In fact, I think I set those ones last week. Okay, if you haven't done 15 to 18, because they're all based on quantum numbers, you'll be able to do them now. Okay, let's have a look at something called the ground state configuration. There are certain rules when you're doing the electron configuration. The ground state configuration is the lowest possible electronic configuration. It's basically the lowest energy state. One of the rules that you have to follow is called the Aufbau principle. Okay, anyone who's done German, Aufbau means building up. This states that you have to fill the orbitals in order of increasing energy. You can't fill higher energy levels before you fill the ones of a lower energy. The order of increasing energy starts with the 1s, so it has the lowest energy, followed by the 2s, followed by the 2p, the 3s, the 3p. Now this is where it becomes unusual, because 4s actually has a slightly lower energy than the 3d, and that's important to remember. So the 4s fills before the 3d, and we move on to the 4p and 5s. We're likely to do anything with the 5s orbitals. So again, the key point to note is the fact that the 4s orbital has a lower energy, so is filled before 3d orbital. Okay, this is just the same thing represented in the diagram. So in the first energy level, there's only the 1s orbital. In the second energy, there's the 2s orbital, and then 3 2p orbitals, px, py, z. In the third energy level, there's the 3s and the 3p orbitals. And you know the 4s, which is in the fourth energy level, but it has a slightly lower energy than is 5 3d orbitals. When you've got an isolated atom, orbitals within each subshell are degenerate. Remember that degenerate means they have the same energy. So these 3 2p orbitals have the same energy. These 3 3p orbitals have the same energy as each other, and the 5 3d orbitals have the same energy as each other. Another rule that must be followed is Hund's rule. What Hund's rule states is that where there's degenerate orbitals available, the electrons will fill singly, keeping their spins parallel before spin pairing starts. If we have a look at carbon as an example, so carbon is 1s2, 2s2, 2p2. So we filled the 1s, we put one electron in. Then we put another electron in with the opposite spin. It's orbital, put one electron in, and then another electron in with the opposite spin. With the 2p subshell, we have 3 degenerate orbitals, so the electrons will fill singly. So the first electron goes into the first p orbital. The second electron goes into the second p orbital with a parallel spin, so the spin will be the same direction as the first one. And this applies to Hund's rule. If we had something with a third electron, you would put the third electron in the third p orbital, again with a parallel spin. If you had a fourth electron, it would go back and fill the first one with the opposite spin. Remember, each orbital can hold 2 electrons. So the Pauli exclusion principle, no 2 electrons in one atom have the same 4 quantum numbers, so therefore no orbital can hold more than 2 electrons, and these 2 electrons must have opposite spins. Okay, I ask you to complete the table on this page. Now this is going to be impossible to do in this format, so what I've done is created a separate document to help you do the electron configurations that are on page 13 and 14. So you should use that document to be able to complete these. Okay, obviously you should always label which box is which. Okay, so this is the 1s for hydrogen. Here's helium with a second electron in the 1s orbital. Lithium is 1s2, 2s1. So 1 electron and then an electron with an opposite spin in the 1s orbital, and then in the 2s orbital there's 1 electron. Beryllium, we just add another electron into that 2s orbital. For boron, the 1s and the 2s orbitals are full, and we start to fill the 2p orbitals. For carbon, the 1s and the 2s are full, and then we have 2 electrons in the 2p orbitals. Nitrogen, you can see the 3 parallel spins obeying Hund's rule. For oxygen, that 4th electron is going to go into the first p orbital with an opposite spin to the electron that's already there, and so on. Working through these elements, you just add an electron each time. Once you get beyond, back to sodium, you need to move into the 3s orbital. Okay, on the next page, this time you've got some more complex elements to do. Okay, some of these are ions as well, further down. Take care because that bromide one is quite difficult to see. Again, there's a document for these to be able to complete. Now, for any of the ones that are basically scandium and above, you can use the noble gas shorthand, and that's been shown in the document that you can complete. The reason is because you're going to end up, if we write all the way from 1s to 4s or 4p, then you're going to use a lot of boxes. So there's a short way of writing them. So now, after following that, you can do questions 19 to 23 in your notes. We'll have a look at the blocks of the periodic table. Now it's divided into 4 blocks: the S, the P, the D, and the F. And it corresponds to the outer electron configurations of the elements within these blocks. For example, okay, this here is called the S block, and you are filling s orbitals for the elements here. So for example, hydrogen has 1 electron in the 1s orbital. Lithium has 1 electron in the 2s orbital. Beryllium has 2 electrons in the 2s orbital. Okay, the exception is, note helium over here. It's kind of over beside the p block, but it's actually a member of the s block because you put that electron into the 1s orbital. This block here is the p block because you're filling the p orbitals as you move through this block. The transition elements are called the d block. And then the lanthanides and the actinides are called the F block. We're not going to deal with the F block in advanced hard chemistry. So the 4 blocks are S, P, D, and F. There have been questions based on this. The one that catches everyone out is asking about noble gases and if which orbital is filled for a noble gas. And you have to remember that for helium it's S, but for the rest it's a P orbital that's filled. We can use these electronic configurations to help explain some unusual irregularities in ionization energy. Now, you've met ionization energy in higher, and you've kind of done general trends, but we're going to have a look in a bit more detail. So this is just the general equation for the first ionization energy and the second ionization energy. This graph shows the value of the first ionization energy from atomic number 1 to 38. Okay. We should know, hopefully, that ionization energy increases across a period due to the increased nuclear charge. Okay. The outer electrons experience a greater attractive force from the nucleus, and that's why it increases across a period. We also know that ionization energy decreases down a group, and that's because the outer electrons are further from the nucleus, and they experience a shielding effect from the inner shells. We know that the ionization energies of the noble gases are the highest because your electron has to be removed from the full outer shell. The ionization energy of the alkali metals are the lowest, and the reason is because there's only 1 electron in that outer shell. What we haven't looked at are these abnormalities in the shape of the graph. So going from beryllium to boron. Okay, now beryllium has an electron arrangement of 1s2, 2s2. Boron has an electron arrangement of 1s2, 2s2, 2p1. Okay, so what actually has happened here, the reason why beryllium's got a slightly higher ionization energy is because you have to remove an electron from a full 2s orbital. So there's a kind of additional stability associated with that. With nitrogen and oxygen, the electron arrangement of nitrogen is 1s2, 2s2, 2p3. Oxygen 1s2, 2s2, 2p4. Now what nitrogen has that's unusual, and it gives it a special stability, is it's got a half-filled subshell. So because it's 1s2, 2s2, 2p3, those 3 electrons in the p subshell means it's half-filled, and it gives it a special stability. So this happens when the p subshell, when it contains 3 or 6 electrons. It also happens with the d subshell when it's got 5 or 10 electrons in it. The more stable the electronic configuration, the more difficult it is to remove an electron, and so therefore the ionization energy will be higher. Okay, so as we have said, the ionization energy changes across a period. Ionization energies for the noble gas are the highest because you have to remove the electron from a full outer shell. We can explain the decrease in ionization energy between boron and beryllium, and that was because of the electron arrangement. Beryllium is 2s2, so it has a full 2s orbital, and you have to remove an electron that's slightly more stable arrangement, and so therefore it requires more energy. We can also explain the decrease in ionization energy between nitrogen and oxygen, because the nitrogen has that unusual characteristic of having a half-filled p subshell, and therefore it has a special stability, which means it requires more energy to remove an electron from that arrangement. So this happens with the p subshell when it contains 3 or 6 electrons. 3 would be half-filled, 6 would be a full subshell. And with the d subshell, it happens when it contains 5 or 10 electrons. And as we said, the more stable the electron configuration, the higher the ionization energy. You should now be able to answer questions 24 to 27 in the ionic chemistry section. Inorganic chemistry section. There will also be a check test on this on Google Classroom. If you have any questions, please ask either at the tutorial or at any other time, comment or send an email. Thank you.